Welcome once again to my channel. This is Tishatari. In our previous lesson, we treated what is known as oxidation reduction reaction, known as redox reaction. In today's topic, we'll be talking about introduction to organic chemistry. We're going to talk about the basic terms in organic chemistry. So the word organic, before now, we have been hearing this word organic. We have heard of organic cream, organic soap, and so on and so forth. What we mean by organic, it means something that is natural. Before now, so what we mean by organic chemistry in a normal originally mean compounds that are formed from either plant or what? Or animals. So in this aspect, but some of these organic compounds are synthesized from inorganic compounds. So a very simple and concise definition of organic chemistry is the chemistry of carbons and some other element that is attached to carbon. Example is hydrogen, have hydrogen, sulfur, oxygen, nitrogen, and so on and so forth. So a very simple and concise definition of organic chemistry is the chemistry of carbon and other elements that is attached to carbon, such as hydrogen, sulfur, oxygen, and nitrogen. That is to say, carbon have these unique characteristics that makes it to be very popular in the world. So what I mean by the uniqueness of this carbon is that it has the ability to form a very long chain or branch chain. That is to say, it undergo what is known as catenation. Catenation. So this is the ability of carbon to form long or branch chain. That is why we have a lot of organic compounds in our environment. That we also say that carbon have the ability, it is open to three hybridization. So that is to known as hybridization. It is open to sp3 hybridization. It is open to sp2, and it is open to sp. These characteristics give you the idea of undergoing of having, that is of bonding to single bond. It has the ability of bonding to double bond. It has the ability to be bonded with what? With three bonds. So these unique characteristics of carbon makes it so popular. We also talk about the unique configuration of this carbon. We said the electronic configuration of carbon is 1s2, 2s2, and 2p2. So the atomic number of carbon is 6. It says, we said carbon have a unique characteristics because it has two electrons in the p orbital. That is to say, when this carbon is excited, let's use according to Hund's rule, let's use this aspect. We said we have three types of this p orbital. We have three types of p orbital. In this regard, we are going to have the ps, we have the py, and the pz. That is to say, if on a Cartesian plane, the orbital that is formed on the s-axis is known as ps, the one that is formed on y-axis is known as py, and the one that is formed on the z-axis is known as what? Pz. So that is to say, we have these three types of p orbital. So the shape of p, or this p orbital, is a dumbbell. It has a dumbbell shape. So it has a lobes that is opposite to each other with the center. That is to say, it has a dumbbell shape like this. That is to say, it has a dumbbell shape. So we're going to illustrate how this PS came about, this PY came about, and this PZ. That is to say, for us to explain the configuration of this carbon, we must have this ideal. So it is an origin. Let's say this is Y, this is S. The one that is formed on this Y-axis is known as, let's write here, py. So we have the one Let's wipe this. We'll come back to that. The one that is formed on this S-axis is known as PS. So the one that is formed on the Z-axis, on this Z-axis, we said it's known as what? PZ. PZ. So in this aspect, this is just the structure of each of these orbital, PS, PY, and the PZ. So we're going to move to the electronic configuration of carbon that makes it very unique to be bonded tetrahedrally. We say carbon is very unique because it is bonded tetrahedrally. How come about that it is bonded tetrahedrally when it has only two electrons in the p orbital? So let's have this electronic configuration of this. We say the P has three types. We have the two P here. We have the two S here. We have the two S2, two S2. So that is to say, using Ohm's rule, we said they're going to arrange this electron. Let's arrange this electron. Let's arrange this electron. We said, according to Ohm's rule, that electron will fill singly. The electron will fill each of these space singly before pairing can occur. That is, all if this is during this the ground state of carbon. During an excitation state, one of these electrons is promoted to fill this empty shell. That is to say, we are going to have, in this regard, we're going to have same energy level. We're going to have this electron will fill this empty shell, leaving this the 2s left with one electron. The 2s2 is already filled up. That is to say, carbon have this 1, 2, 3, 4 shell to be bonded. That means we said it can be bonded tetrahedrally. It needs 4 electrons to be octet to complete its shell. So having known this now, we are going to move to the basic terms in organic chemistry. What are the basic terms that will keep on reoccurring throughout this topic? What are the basic terms that will come to our mind every time we talk about organic chemistry? Talk about terms in organic chemistry. Terms in organic chemistry. So we're going to run through the terms. One of them, we're going to talk about homologous series. Homologous series. Homologous series. So we're going to talk about 2. We're going to talk about alkyl group. Alkyl group. We're going to talk about 3. We're going to talk about functional group. Functional group. Functional group. I'm going to talk about, let's talk about hybridization. Hybridization. I think we're going to have a separate lesson on this hybridization so that we explain the basic concept. After this, we talk about isomerism. Isomerism. So, sixth, we'll talk about the structural formula, the arrangement of these atoms. Structural formula. So we're going to start with this homologous series. We define a homologous series is a series of organic compounds. It's a family of organic compounds that follows a structural pattern, and in which each member differ by a CH2. What we mean by a CH2? A CH2. Each of these successful members differ from each other by a CH2. What we mean by this? I'm going to explain this concept promptly. So what we mean about homologous series, we define homologous series is a series of organic compound or a family of organic compound that follows a structural formula, that follow a structural pattern. In this regards now, each member differ from each other by this CH2. We said, for instance now, if I'm able to identify the first member of any organic compound, I should be able to know the next member using this CH2. By so doing, if for instance now, let's have an alkane family. We said a very good example of this alkane family. Let's make use of methane. Methane have a molecular formula of CH4. We said this is the first member of alkane family. We said we have two. We're going to have ethane. Ethane. The next one, I'm going to have propane, three carbon alkane. So by so doing now, if for instance, if I should add this series, this homologous series CH2 to this, it's going to give me the molecular formula of the next member. Carbon plus carbon is carbon 2. Hydrogen 4 plus hydrogen is 6 hydrogen. We have 4 hydrogen here plus this 2 is 6 hydrogen. This is the what? This is the second member of this alkane family. So if I should add another CH2, it's going to give me the next member. C2 here plus 1 here. You're going to have C3. We have 6 hydrogen plus 2. You're going to have C8. So as I continue to add this CH2 as a family, I'm going to have the next successful members accordingly. So by so doing, we say they differ from each other by a CH2. A CH2. In some question, they will define that homologous series is a series of organic compounds that follow a structural pattern, and they differ by what? They differ by what? This group, CH2 group. So we're going to talk about alkyl group. Alkyl group is obtained when an alkane family loses an electron and is given by a molecule, a formula known as CN H2N plus 1. That is to say, let N represent the number of the member or the number of each of the successful members. For instance, now like methane that occupy number 1, we can say let N is equals to 1. I'm going to have C1 H2 times 1 plus 1. C1, 1 times 1 is 2 plus 3. You're going to have CH3. So in a normal definition as well, in other way, we can say when an alkane family loses an electron, let's use methane. When methane loses an electron, it's going to give us CH3. Since this is known as methane, if this is known as methane, since we can change this place, can replace this place with YL from the alkyl. So in this case now, any compound that any group that started with CH3 is known as methyl. It's known as methyl. So by so doing, when the next member of this alkane family loses an electron, let's use a very good one. Let's have ethane, for instance, the second member. In alkane family, is a molecular formula is C2H6. C2H6. So when it loses an electron, C2H6, when it loses an electron, it's going to give C2H5. By so doing, if we should replace this ANE with YL, I'm going to have ETH, ethyl. So ethyl is given that. So when we have the next member as CH8, when it loses an electron, we're going to have C3H7. This is what? This is known as, since we have propane here, propane, we're going to remove this ANE to have YL, that is propyl. So by so doing, when an alkane family loses this electron, it gives what is known as what is known as alkyl group, and it is denoted, and this alkyl group is denoted by a capital R, by capital R. If I'm writing a chemical, a structural formula of organic compound, and when I said this, that we have something like this, we have R here we have R. It means that this R means an alkyl group. It can be CH3, it can be C2H5, it can be C3H7. Any of these alkyl group represent this symbol known as alkyl. We use R to represent this alkyl group. Alkyl group. So this foundational topic in organic chemistry, you must know these terms so that this aspect of chemistry will be very easy. Will be an easygoing topic. So we'll talk about the functional group. We'll talk about functional group. They are atoms or group of atoms or radicals that what that that when it determine the chemical properties of this compound. So by so doing, they are in form of bond that is common to this homologous series. That is common to homologous series, and they determine the chemical properties of this compound. So the functional group just is in a simple terms, just like our various surname in the class. If for instance I'm having the umokoro in the class, if anytime I mention umokoro, we should be able to know the group of persons I'm trying to talk to. If for instance I'm having like 3 to 4 umokoros in my class, each time I say umokoros should stand up, they believe that whenever I mention that surname, they know that I'm calling on them on a specific task. So on this now, we have these functional groups tell us just like a family name of each of these organic compounds. A very good example, let's wipe this. So we are going to have this functional group. If for instance, the functional group of this alkane family, let's say alkane, for me to identify this alkane family, can alkane family have a single bond? If we say alkane family have this double bond, yeah, we should have an alkyne, they have this triple bond. If for instance I'm having a compound like this, it means that here I'm talking about the because of this presence of this double bond, it is this triple bond is known as alkyne group. So if I'm having a compound like that have this double bond, I'm talking about the alkene family, the alkene family. So this is just like our surname in a classroom, for instance. So it tells us each of these group, that is each of these organic compound that we have. So the next one, let's talk about each of these functional group. We should have something like this. OH, we have this. This is known as alkanol. This is known as alkanol family. So we should have something like a C. We say this is what? Alkanoic family. Alkanoic family. So if we should have a C, we have H here. This is known as alkana family. A very good example is the aldehydes. Other name for this is known as aldehydes. Aldehydes. So if I should wipe this as well and say what is this? This is known as alkanol. Alkanol family. Alkanol family. So we have something that we have R O when we have R here. Is there? This is ethyl. These are ethyl family. So whenever I see this kind of structure, I should be able to understand that this atom or group of radical, they have a specific name or they are tied to a family known as ethyl. So for instance, now let's move on. Let's talk about, we have so many of them. When we have, let's say we have CO, we say this is what? Esters. So we have the imine. We have the imine. Let's say the imine. This is the imine. This is imine. We're going to talk about the amines. The amines are just like this. So each time I see this kind of group in an organic compound, I know it's from a family of amide. So to round it up, we say this functional group, they're in form of just represent our phoneme, our surname in our environment. So when they call upon your name, you should be able to answer, Mr. Atari, where are you? I will say, I'm here. That is just my representation to show that I'm answerable to such names. So this radicals represent each member of this family. We have so many of them. We are going to make use of throughout this course of this organic chemistry. We know more about this aspect of chemistry using the functional group. So we are going to talk about hybridization. Let's talk more about hybridization. We said carbon is open to sp3, open to sp3, open to sp2 and sp. This give carbon the ability to form single bond, to form double bond, to form triple bond. So since carbon is open to sp3, sp2 and sp, it gives us a very clear understanding of what happened. So for us, let's dive deeper on how this sp3, sp2, sp comes about. We said when every element in the periodic table, their aim is to be stable, to have this octet structure. When we're discussing about a chemical combination, we said this element come together so that they can achieve what is known as octet structure. To achieve what is known as octet structure. So by so doing, this hybridization occur in such manner as well. So we said we define hybridization as the missing or overlap of two or more orbitals in the same principal quantum. So that is to say, to give a new orbital. This new orbital is known as hybrid orbital. And this hybrid orbital will give us types of bond that exist in organic compounds. Now we are going to talk about the sigma bond and the pi bond. So we said, if we are going to discuss this about the sp3 hybridization, we said we have one S and 3p came together. That is to say, if parametric, let's use a very good example. Let's use a electronic configuration of carbon. We said have one here, and two. We said this carbon is in excited state. So for us, for this, we have the one S, 2S, and the 2P. Here, we say one of these S is used for bonding. The one of these S is used for bonding. By this case, this should be very close to the 2P because the character that is contributed by S is 25%, while that is contributed by P is 75%. So this orbital is closer to this 2P. That is this three electron here are used for bonding. So this one is contributed. This three is contributed. This one that is formed here, this new orbital that is formed is known as hybrid orbital. That is known as hybrid orbital. So let's talk about the sp2. The sp2 means that one S, sp2, we said it means that one S is contributed and 2p is contributed. By so doing, the character that is contributed by this p is around 67, while that is contributed, the character that is contributed by S is 33%. To make it 100%, we are going to use the same example. When we have something like this, the electronic configuration of carbon, here we said they are all in excited state. Yeah, they are all in excited state. So when we have this, we said since we have 67%, there the orbital that will be formed will be it will be closer to this S as well, but not as close of this orbital to the 2p. So here, since the character is contributed by S is 33%, it will be more lower compared to this. So here we said we're going to have one S is contributed. We said we have 2P. 2P is contributed. That is to say, one of these P is not bonded. So this is known as hybridized orbital. We said we have 3P in carbon atom. By so doing, one of these electron is not used for bonding. So this one that is not used for bonding is known as unhybrid orbital. Hybrid orbital. So this hybrid orbital, this is what organic compound use to produce what is known as sigma bond. Sigma bond. So why this on hybrid orbital? This our organic compound using to form what is known as pi bond. Pi bond. So for a more deeper explanation on this hybridization, I'll take a time. I'll take a very simple lesson so that we'll talk more about specifically on this hybridization. So in this SP contributed one character, 50% character, because it's SP. This contributed 50% character. So here, two of these P will not be used for bonding here. In case of SP, two of these electrons will not be used for bonding. In this aspect, we are going to have unhybridized orbitals where two unhybridized orbitals. So this most of the time we use this one for pi bond. So every single bond in organic compound, they make use of this sigma bond. Every single bond contains what is known as sigma bond. So for us to identify this pi bond and sigma bond, we should be able to know the double bond. So when we have a single bond, we say sigma bond is here. Always use here we must have one sigma bond, one pi bond here. Here we're going to have one sigma bond and two pi bond. So that's how it is arranged. So I will take a specific time to explain this concept in a very separate video so that we understand what is known as hybridization in advanced term. So the next subtopic we're going to talk about isomerism. We define isomerism as the existence of two or more compounds with the same molecular formula but different structural formula. They have the same molecular formula but different structural formula. So what happened here, when they have the same molecular formula but different structural formula, what is produced at the end is known as isomer. What is produced at the end, they are known as isomers. So isomer, the carbon, as the carbon increases in organic compound, the probability of having many isomer is very possible. So as the carbon increases, the possibility of having more isomer is very possible. So that is to say, isomerism is very, very important. It's very, very common with an alkyl family. Most of the organic compound, they are the alkyne. So a very good example, if we should have this compound, for instance, let's have this compound, say, we have methyl group here. We have hydrogen here. In this case, we have, this is known as 4 carbon hydrocarbon, or organic compound like butane. Because of this structural arrangement of this hydrocarbon, this carbon can be named as, let's number from here, 2, 3. We can name this compound as 2 methyl 2-methyl propane. You can see that because of this structural arrangement of this compound, we have arrived at this compound. Instead of saying this is butane, I mean. So in this aspect, isomerism increases when the number of carbon increases. So we have two types of isomerism in this regard. We have two types of isomerism. Two types of isomerism. I'm going to talk about two types of isomerism. We have the geometric isomerism and the optical isomerism. So the geometric isomerism is the existence of two or more organic compounds. They have the same molecular formula as well, but they have different spatial arrangement. So under this point, I'm going to talk about two types. We're going to talk about the cis isomerism and the trans isomerism. So when we have, we can use a but2n to explain this concept. Let's use but2n to explain this concept. So if we should have compound like this, when you have these two heavy molecular group on the same plane, when I have this heavy molecular group on the same plane, we say this kind of configuration in geometry is geometry isomerism known as cis. If I want to name this compound, I will say this is cis but 2n. This is cis but 2n because this heavy molecular group is found on the same plane. So when they are found on opposite side of each other, it is known as trans. Let's have a very good example of that. A very good example. That is just all about trans and cis. We said when this heavy molecular group, they are opposite each other. When this heavy molecular group, that is the methyl group, they are opposite each other. This is known as trans isomerism, which is isomerism. So since this heavy molecular group and this, they are opposite each other, this is known as trans isomerism. For me to need it, I will say trans both 2n. So the most of the features in this characteristics that the physical properties of these compounds can be affected with this configuration as well. So we are going to talk about optical isomerism. So optical isomerism, you learn more about optical isomerism when we are talking about carbohydrates. So when we talk about optical isomerism, we'll talk about the existence of two or more organic compounds. They have the same molecular formula, but they have different optical configuration. And this compound, they have the ability to what? To rotate polarized light. So we say polarized light are those light waves that vibrate, have a vibration that have a vibration on the same plane, or they vibrate on the same plane. We said these are light waves that vibrate on the same plane. So by so doing, for any compound that rotate this polarized light, we said this compound, they are known as optical active. They are optically active compounds. And for organic compounds to be optically active, it must be bonded to 4 different substituents. For instance, now let's have a very good example. For a compound to undergo what is known as optical isomerism, or to be optical active, the carbon must have 4 different substituents. Let's use the COH. We have the OH. Let's have the HCl. Let's have the methyl. A very good. This is known as lactic acid. Lactic acid. So by so doing, this carbon that is bonded, for a compound to be optically active, the carbon must be bonded to 4 different substituents. You can see this is bonded to COH, this is bonded to AOH, methyl group, and the hydrogen. So there are asymmetry to each other. So in this now, if we have, when we talk about optical, talk about mirror. So the mirror image of this, we are going to have hydrogen CCA. Here we are going to have HO. Here we are going to have CH3. Let's have H3C. Here we are going to have hydrogen. So it's just the mirror image of this compound. So we said this compound must have a carbon that is bonded to 4 different substituents for any compound to be optically active. So when any compound that rotates this polymerized light to the right hand side, this polymerized light to the right, we said such compound undergo what is known as death-through-rotatory. They are known as death-through-rotatory compounds, and it is denoted by D. So when a compound polymerize or rotate this polymerized light to the right, we said such compound is known as death-through-rotatory compound. It is denoted by D or positive. So when this polymerized light is rotated to the left, it is known as Laval rotatory. It is denoted by L or negative. So by so doing, we have achieved most of the point today. Let's talk about the structural formula. A very simple. What are structural formula? Structural formula is the arrangement of this molecular formula in a structural way so that we can show each of the bond that is present in an organic compound. Let's say we have CH3, CH2, CH2, CH3. In this aspect, we say this organic compound contains, for us to have a structural formula, we want to show how these hydrogen and carbon to carbon bonds are arranged. We say we have 4 carbon. We say the first carbon, it is bonded to 3 hydrogen. We say it is bonded to 2 hydrogen. Here it is bonded to 2 hydrogen. Here it is bonded to this, and this. The process of showing this arrangement is known as structural. This is structural formula of the above molecular formula. Structural formula. So this is the end of this lesson. If you should like this lesson, please do well to subscribe to this channel and share to your friends so that they can see this video. Thank you.